Hi, this is David Voss, CCIE 11372, and in this video you're going to learn about EIGRP design. We're going to do a high-level EIGRP overview in this video, and then we're going to talk about the EIGRP components. You're going to see this constant theme of these four components. So first, there are EIGRP messages that are unique to EIGRP. There's a unique EIGRP algorithm. There are tables that are, again, unique to EIGRP that you need to know about. And then finally, you need to know that EIGRP supports independent modules. So there's multiple support for multiple different network layer protocols. Now, the way we're going to approach this is, again, it's a high-level overview of concepts that are unique to EIGRP. So we all know that EIGRP can support VLSM, for example, but many routing protocols can. So we're not going to dig into VLSM and EIGRP. We're going to talk about things that are unique to EIGRP. Now, to understand EIGRP, we first need to understand IGRP. IGRP came out in 1986. It is an interior gateway protocol that was once very popular. Distance vector routing protocol. And it used four key attributes to develop this distance information on how to choose the best path. So it looked at the link, and then it said how much available bandwidth is there, how much delay, how much load, and how much link reliability is there on this link path or on the multiple links to my path. Well, EIGRP is still an interior gateway protocol, and it is still a distance vector protocol, although many times in the past it had been referred to as hybrid, but those days are pretty much gone. Distance vector is what it's classified as, but it has improved convergence in operations. So it uses the dual diffusing update algorithm, and I'll show you about that in a few minutes. And then again, it has multiple unique tables to EIGRP, which assists in the operations and enhances the operations. And then again, it supports multiple network layer protocols. So how does EIGRP actually work? Well, I tell you what, let's go ahead and open up the hood and take a look underneath. EIGRP has four basic components, and these should already start looking familiar to you. It has messages. So messages flow to and from neighbors, EIGRP neighbors. There's 5 different types. We'll dig into that in a little bit. EIGRP has the dual algorithm. The dual algorithm takes the information from those messages and then processes best path and possible best path. Then all the information from the messages and the algorithms get put into tables. So these EIGRP tables hold the data from the algorithm and the messages. And then finally, the modules. These protocol-dependent modules support a variety of network layer protocols. So we're not limited. EIGRP is not limited to just IP. So with regards to messages, there are different types of packet formats. There's 5 different types of packet formats. First, there's the hello message. A hello message is basically a query out to anybody who'll listen, asking if anybody's out there. So a router running EIGRP sends hello packets by default, and it will send those packets out and hope for a return reply. And when it gets a return reply, it'll get that update. And that update contains all of the messages or all of the routes that want to be shared via EIGRP. Update messages are messages with a lot of routing information in them. And then there's the acknowledgement message, which surely you know about from other protocols, but it's simply acknowledging that, yes, I've received your message. And that's key to the reliable nature of EIGRP, which we'll talk about in a minute. There's a query message. So if EIGRP loses a route and does not know how to get there anymore, it will query its neighbors saying, do you have any information about this route? Because I'd like to get that information. And then if a router does have information on that route or on that path, it will reply back saying, yes, I do have information, and here it is. So these 5 messages can be broken out into 2 categories, some that are reliable and some that are not reliable. The reliable messages use reliable transport protocol, and this is unique to EIGRP, but RTP basically makes sure that packets get to where they're supposed to go in order. So an unreliable packet is a hello message. That message is not reliable, but the update message from an EIGRP router does use RTP. So it is sequenced and there are acknowledgments. So there is an acknowledgement to that message, but the acknowledgement itself is not reliable. Then there's the query message. Remember, the query is to ask, do you have information about this route? And that uses RTP, and the response to that query, the reply, also uses RTP. So 3 different types of messages use RTP: the update, the query, and the reply. And I think that's critical to know for your exam. Now let's talk about the EIGRP algorithm, which is dual. Now, to understand dual, you need to understand what successor and feasible successor routes are. When you think of successor, just think of success. That's the best path. So if EIGRP loses connectivity to the best path, it will then run the dual algorithm and ask, is there a feasible successor? Is there a second best path? And if the dual algorithm states, yes, there is a feasible successor, a second best path, it will then promote that second best path to the best path. So that becomes the successor. Once it's the successor, it is then installed into the routing table. So for example, it would be installed into the IP routing table. And then the router would begin to use that new path. So this chart gives you an overview a high-level overview of how the dual algorithm runs. But it's important to know these concepts of successor and feasible successor as you move forward with EIGRP and how dual uses that information. Now, EIGRP uses specific tables to help make it run, and one of the tables that EIGRP uses is called a neighbor table. Now, a neighbor table is exactly what you think it is. It's a table that is comprised of a listing of all the EIGRP neighbors. So, for example, we have a hub and spoke design here. We have router A, router B, and router C. And router A and router B are both running EIGRP. Router A sends out a hello packet, and router B responds back as well, and they've established a neighbor relationship, and router A sends out a hello packet. Router C does the same, and they've established their EIGRP neighbor relationship. So once that happens, router A begins to build out its neighbor table by identifying each neighbor by IP address. So for example, router B is 172.16.1.1, and he gets placed into the neighbor table. And then router C is 192.168.10.2. and he is placed in the router table as well. So router A now has 2 neighbors, and they are both listed in its neighbor table. But there's also other information in the neighbor table as well. And the router A also wants to know what interface are these routers off of. So router B is off of serial 1, router C is off of serial 2. So should I need to forward them traffic, or I know exactly which interface they will be exiting. And then finally, there's other information that is entered into the neighbor table. There's quite a bit actually, but for the sake of this high-level overview, let's just talk about hold time, because this is a key concept. When you program hold time on a router, it's not local. You're not changing the hold time locally. That information is actually forwarded over to your neighbor routers. So here we have router C, who's changed his hold time to 10 seconds. He forwards that over to router A. And here we have router B, and let's say he's going to change his hold time. This information that they're changing from the default, it gets inserted into the neighbor table on router A. And remember, hold time is basically telling the router, if you don't hear from me in this amount of time, consider me down and flush the routes that you receive from me. So it's important to remember hold time is configured on router C and router B, but the actual numeric change occurs on router A in the neighbor table. Now there's definitely other attributes that are in the neighbor table, and we will definitely go over those in future videos. But on a high-level overview of EIGRP, you need to know about the IP, the interface, and the hold time counter. And just remember, hold time defaults is 180 seconds for low bandwidth links and 15 seconds for T1 or higher. So that'll come up again and again, and you'll probably be asked about that as well. But there are other EIGRP tables that you should also be aware of. And a key table to know about is the topology table. Topology table contains all destinations advertised by neighboring routers. This includes, remember, the successor and feasible successor routes, the best path to a destination and the next best path, respectively. So topology table is key for EIGRP to run. Now remember, within topology table, you can see the route tags. So in EIGRP, you can actually perform route tagging. And all you really need to know for now is that you can identify routes by their origination, which allows for custom routing. So you can tag those routes with a manual entry. So that's all you really need to know for now. But getting back to EIGRP tables. Now, here's an example. We have, again, a hub and spoke design, router A, router B, and router C. Now, router A is going to build out, as soon as it enables EIGRP, it's going to build out these EIGRP tables. And one of the tables, again, is going to be this topology table. The topology table is going to contain critical information for EIGRP to run and make the choices upon what the best path is going to be. So in the topology table, it's going to insert routes that it learns from router B and router C. And then it's going to ask, now that I know about this route, which neighbor did I learn it from? And then finally, it's going to say, all right, I know the route, I know the neighbor I learned from, what metric should I assign to it? Which way should I send traffic or forward traffic? So in this example, the route itself, let's say we'll do a 10.1.1.0/24. And let's say we learn this route from both router B and from router C. So this topology table is filled out with 2 entries for the same route. Again, this is not the routing table yet. This is the topology table. And it has a metric, so let's keep it simple. So the metric to router B is 10, and the metric to router C is 20. So for this simple example, let's just say that the router now realizes that the successor route, the best route, is going to be the path through router B. Now, once the dual algorithm has run and it realizes this, it then takes that route or that path and it places the successor route into the routing table, in this case the IP routing table. So now we know the successor is to router B and the feasible successor path is to router C. So as we can see, it's going to choose the path out to router B. Now, what happens if this route information is lost and router A no longer learns about this route from router B or from router C and it gets flushed? Well, router A, what he's going to do is he's going to send a query to router B and to router C asking, do you know about this route? Because I've lost it and I'm hoping you have information on it. And the neighbors will respond back, but specifically, let's say in this case that router C is the only one that knows about it. Router C will respond, yes, I'm aware of it, and it will send the information over, and router A will say thank you very much, and router A will then insert it into the topology table. It will become the successor, and once it's the successor, it will be placed into the routing table. And then router A will then begin using the path through router C to reach that subnet. And last, but certainly not least, we have protocol-dependent modules. So EIGRP and the dual algorithm function in a way that protocols can run and use EIGRP independently of one another. So IP builds out its own neighbor and topology tables. IPX and AppleTalk, they all build out their own neighbor and topology tables, and dual can work with any and all of them. So you've learned a lot in this video that will help you with EIGRP design. We've done an overview and we've talked about the individual components of EIGRP, messages, algorithms, tables, and modules. You'll need to know all this information not only to design EIGRP, but obviously to do very well on the CCDA exam. If you study what's in this video and know it well, I'm confident you'll do really well in the EIGRP portion of your CCDA. Good luck in your studies.